That he came back in France, and he leads after for the Qatar Foundation and the Texas A&M University of Qatar. He developed numerous new results and new modeling in multiscale modeling, in crystal plasticity, mechanics of polymers and composites, and with a lot of application in processing, for instance, in energy, etc. So now, Professor Saïd Ahzi, you can present your result. Thank you very much.
Thank you, Yves. Thank you, Yves, for this nice presentation. And I'm pleased and honored to be here and present some of my work in collaboration with many colleagues and graduate students. Is it working? Yeah, okay. So,
c'est très directionnel, donc
okay. Donc, as the title says, I will talk about micromechanics of materials as well as multiscale modeling and homogenization, and of course I will focus on microstructural effects, existing microstructure and the evolution also of the microstructure, and how that affects the properties. So the applications that I will focus on today, one is on crystal plasticity, the second is application to polymers and polymer nanocomposites, and the last one, but not least, the application to biological materials in terms of homogenization and prediction of the effective properties. So let me start with the crystal plasticity part, and I will go through a very brief introduction. Then I will talk about the viscoplastic formulation of deformation of single crystals, then polycrystal, and how we average to get the macroscopic response, but to get also the evolution of the microstructure. And I will talk about the self-consistent modeling. I will talk about the self-consistent like model, which is a more pragmatic way of homogenizing, but it gives us also great results. It is simpler than the self-consistent, but I will show you that we predict nice results from that model. And I will also compare to the classical upper bound and lower bound estimates. So the motivation for crystal plasticity is the fact that when you have deformation processes like in metal forming, well, you may have initially an isotropic material, but at the end you will have an isotropy that is due to morphology change, the shape of the grains and their orientation, also some behavior that is due to grain boundaries, but mainly what I will focus on is the crystallographic orientation, okay? That we call texture or preferential orientations of crystals. So as is shown in this schematic here, you may have an initially random distribution of crystallographic orientations, but after a process like a rolling or forging or so, you will have highly oriented material, and you have different orientational components that we call texture components or preferential orientation components. So plasticity happens by or occurs by crystallographic slip on specific crystallographic planes and crystallographic directions depending on the crystalline structure that you have. It may happen also by twinning, okay? So these are the main mechanisms or microscopic mechanisms that we have to model and account for, okay? And then take this modeling to the macroscopic level. Now, when we deal with microstructural evolution, and here is texture or crystallographic orientation, we need to find a way to represent these textures, okay, or this anisotropy. So one of the representations is through the ODF, the organization distribution functions, which in fact you plot the Euler angles, and then you have the three Euler angles, and each crystal will fit within a point. But this is a 3D representation, which is difficult to read. However, what we could do is have a 2D slice and cut at a given at a given angle. For example, if we take phi constant and then we slice and then we plot the 2D dimensions. However, it's not easy to read except for people that know well crystallography or metallurgy. But the easier way, or one of the easiest ways, is just to use the Paul figures. Okay, either direct Paul figures where you take a crystal, you plot the normal for a given crystallographic plane, and then you project it on the south pole, and when it intercepts the circle, which is the intersection of with the plane that cuts the sphere into a half, that will give you a point. Okay, if you see on the top here, if I have a certain number of crystals, and each crystal will have, for example, if I have an FCC metal, I plot 111 planes, and I plot the normal to 111 planes, and if I see something like this in this Paul figure, that means I have a random distribution. And in this, I have the macroscopic axes are here, 1, 2, and 3. So I know exactly where the crystal sits with respect to macroscopic axis. This is a direct Paul figure. And this is a textured material. This is a rolling texture. Okay? As you can see, this is random. This is rolling. You can see concentration of orientations in specific areas. That means we have preferential orientations. For example, this is the rolling direction. Okay? This is the transverse direction, and the normal direction is in the center. So we can say that if this is 111 Paul figure, then the 111 normal planes will have, some of them will be concentrated around the rolling direction, okay, and some in these areas here. So I'm not going into details of this. The other way of representing is if you have any axial loading, like compression or tension, we use what we call inverse Paul figure. In fact, we sit in the crystal axis and we see how the macro axes rotate. So you plot the 100 for the FCC metals or FCC materials in general, 1 and 111, 100 and 111, and then if you do tensile test, then you may have dots here, and each dot will represent where the tensile axis sits with respect to these 3 directions. Now, I'll start with the modeling of the single crystal, and we are dealing here with large plastic deformation for metal forming. So we go to 100% or more deformation, and we are using large deformation theory. And here, the classical decomposition of the deformation gradient into elastic and plastic that mechanicians know. And I'm using the concept that was developed by Azaro and Needleman in 1985 from Brown University. So we have shearing on a given plane. Okay, that gives you the final configuration here of the crystal that have sheared. And in this final configuration, in fact, the shear plane normal and shear direction have rotated. And they have rotated through this F star here. So in fact, we don't have Fe. Elastic is F star, which includes the elasticity plus the rotation of the lattice. Okay. And then from that, we can, of course, this is the classical decomposition to get the velocity gradient and get the stray rate from the velocity gradient with symmetric part and get the spin, which is the rotation rate, okay? And then the spin can be decomposed into the plastic spin and the lattice, what we call the lattice spin. Now, with this kinematics for the single crystal behavior, let us look at the constitutive law for shearing or for slip or crystallographic slip. So we use a power law. We could use a different law like Arrhenius type relationship because these are thermally activated processes, but power law works very well, and from numerical point of view it's also easy to implement. So this is at the single crystal level. Okay? In FCC we have 12. So the contribution from each of them would be this gamma dot, which is the rate of shearing. The sum of these weighed by the P alpha, which is the Schmidt factor, the symmetric part of the Schmidt factor, which is in fact the cosine directors. Okay? So that gives you your plastic strain rate. Okay, tensor. And in fact, in this law here, the shear rate is related to the shear stress on the given slip system alpha, and of course it depends on the resistance to shearing, okay, or the critical resolved shear stress. And this resistance to shearing, of course, it evolves with deformation. That's what we call strain hardening. Okay? So we have to apply a hardening law for the evolution of this resistance. Now, the single crystal has elastical plastic. So D, the strain rate, is elastical plastic. But since I'm dealing with large plastic deformation, we neglect elasticity. It does not affect at all the microstructure evolution. So we neglect that. D is equal to dP. And if I use the relationship before, then I end up with a relationship like this. So D is MS. M is the compliance tensor, and S is the stress. Now, I have now a constitutive law at the single crystal level. Okay? And then we assume that the macroscopic level for the polycrystal, we assume the similar relationship. Okay? M bar is the macroscopic compliance tensor, S bar is macroscopic stress, D bar is macroscopic strain rate, and then we have to make sure that the global conditions apply, that the averaging conditions, the macroscopic strain rate matches the average of the local strain rates, and the same thing for the stresses. Okay. Now we are done with the constitutive law for single crystal, for the slip system, for single crystal, for polycrystal. Now we need to look at how the local fields, stress and strain of the, or strain rate and stress of the single crystal relate to the macroscopic ones. That's what we call, this relationship here is through an interaction law, okay? And the stressors could be related to macroscopic stress through an interaction tensor, or the same thing for the strain rate. But how to do that? We can make use of HLB tensor, okay? Or go through solving the equilibrium equation, use integral equations, and solve. And then at the end, we end up with this relationship here. This is how D, the local strain rate, relates to macroscopic strain rate in this relationship. So the difference in strain rates is related to difference in stresses. Sorry, this should be S bar. There is a mistake here in the... And this R here is we call it the interaction tensor. This R, in the work I have done with Anna Molinari and Gilles Canova, we found that this R here is N, which is the power coefficient, which is the inverse of the ray sensitivity. This is N, okay, the inverse of the ray sensitivity of the material. It's related to a HLB tensor through this, and M bar is macroscopic compliance tensor, okay? So, and we use the tangent formulation for the single crystal behavior in order to reach this relationship here. A few years later, Lebenson and Carlos Tomei from Los Alamos, they modified this by multiplying by N effective. In fact, what they noticed is if we use the secant modulus, then we will have not N, we will have 1 here, okay? But I'll tell you why we did not, in 87, we did not use the secant modulus, we used the tangent. We knew what the problems was from the beginning. And then we could also generalize it. If we put an N effective equal to 0, then you have the upper bound. What we call in plasticity, we call it Taylor model. But that's the upper bound solution, okay? So now, with this model, you have to deal with the HLB tensor, okay? You have to calculate a HLB tensor for each time step, for each single crystal, especially if you have ellipsoids that are oriented in different directions and so. So we thought of developing maybe a different model, self-consistent, but without having to call for the use of HLB tensor. And one of the motivations also for this, not just only not to use the HLB tensor, is we noticed that texture evolution, when we use self-consistent, then we get results, but that's the only result you get. You don't get any if you get results between the upper bound and lower bound. Upper bound will give you different results, slightly different, and the lower bound will give you also the different result, or slightly depends on the materials. We noticed that for FCC materials, that it depends on the FCC material. You may get results that are close to the upper bound solution, or result at our lower bound solution. And in fact, this is an example of brass and copper, or brass and aluminum, okay? So even though they are all FCC, if you take just this aluminum here and look at the compression texture versus the compression texture of brass, it's completely different, okay? Even though we have this strong component similar, but this distribution around here is not the same. If you look at the same again for rolling, you take copper and you take brass, you see the texture components are slightly deviated from each other, okay? What is the reason? They are all FCC, they have the same slip systems. So there is something that, some old work that has been done to show the effect of stacking fault energy. So stacking fault energy may have something to do with it, which in fact may affect the slip activity and the cross slip and so on within the single crystal. And there might be other reasons that I will mention later on. So that's why we decided to go and look for a different way of developing an interaction law, okay, that links the local field to the macroscopic fields. And what we did here, instead of using integral equations or so, we just looked at the error. If you use upper bound, then you have a huge error in the stresses. If you use lower bound, then you have a huge error in the local stray rates or strains. So we took an error in strain or stray rates, an error in these are quadratics, and then we combined them with this weight function between 0 and 1, the phi, and we call this the phi model. Okay? So we minimized, by the way, I used this d tilde here, d tilde and s tilde, in fact, as what you naively get if you average your local fields. When I say naively, you may not get the macroscopic stress or macroscopic strain. So we have to go through a normalization procedure in order to make sure that your average conditions are met. Okay? And they are related to the macros. These are macroscopic quantities by these tensors that we will evaluate later on. Okay, so, but anyway, we could put D bar and S bar, okay? We just want to make sure that at the end we have the global conditions met as well. So, by minimizing the function, this function, error function, very simple, we end up with this. We end up with D minus D bar or D tilde equals this S minus S bar, similar to the viscoplastic self-consistent. Exactly the same type of writing. The only thing is here we have an sorry, it should be R here. I made a mistake. It should be R. And this is a different R, in fact. This is a different interaction tensor. Okay? So I will not go through these details here. There is no need. Let me just go through this. So this is how we can write the interaction law for both, for the self-consistent and for the phi model. So the difference in stresses are linked to D minus the difference in stray rate through K, which is the inverse of R that I mentioned. Okay? Now, in one case, which is the viscoplastic, the K is either N on N effective times this, okay? Or in the phi model, this is what we get. So we have this relationship, and what we should notice is it depends on the compliance, okay? And the compliance has directionality in it. There is cosine directors in it, okay? Whereas here, the viscoplastic depends on HLB tensor. And HLB depends on the effective properties only, not on the local properties, okay? So, just to show we go to when K go to infinity, we go to the upper bound, when K go to 0, we get the lower bound, okay? Or what we call Sachs and Taylor, okay? There is one more interaction law that I did not mention in the beginning, is how to define the spin. Where in the self-consistent modeling, because we are using integral equations, we are solving for the displacement to displacement rate. We take the symmetric part, we get D, and then we get the antisymmetric part, we get the omega, which is the spin. So in fact, this is what we get for the viscoplastic self-consistent. The local spin, my macroscopic spin, is related to this tensor here, to the differences between stray rates, okay, local and macro. And this is related also to the HLB tensor and so. Whereas in the upper bound, lower bound, or the phi model, well, we have just to impose something, okay? It does not come naturally. So we assume that the local spin is equal to the macroscopic spin, which is in fact in the self-consistent. We have the local spin equal to macroscopic spin if you have spherical grains. If you don't have non-spherical, if they're elongated, then this term is non-zero, okay? The x is non-zero. Now, let me plot these two tensors, the interaction tensors for the phi model and for the self-consistent, and I'm taking the power law or to the power coefficient to be 5, just to, which is in irradiant sensitivity, it is 1/5, and I'm taking phi equal to 0.01, which is close to the upper bound, and phi equal to 0.99, which is close to the lower bound. Okay, so what you should notice here is not necessarily how these things evolve, but what you should notice is the values. Look at the values of k. They are of the order of 200, negative 200, okay? For upper bound, okay? For when we get close to the lower bound, they are very, very small, okay? And in between, of course, they are dropping, okay? Which means that as phi gets smaller or closer to the upper bound, the k is huge, so huge interactions, okay? If we go to self-consistent, it's the same thing. We use the tangent formulation that we developed in '87, secant formulation that Lebenson and Tomei have proposed in 1993, but there is an old paper, in fact, where this exists in 1995. John Hutchinson, okay, from Harvard, developed the secant already at that time, but it was not for large deformation. There was orientation in it, okay, but no texture prediction. So what you should notice is the values again. Look at, for the tangent, the values are of the order of 1. Here the values are 6 times higher, which means that the interactions with the secant modulus are higher. So it's not surprised that I will show you the results with the secant modulus. We got the results close to the upper bound. The other remark here about this interaction tensor here is if we take an ellipsoid within an effective medium, okay, and we take grain 1 here, grain 2. If you look at just the ellipsoid, I'm taking on purpose the same orientation of the ellipsoid, okay? And there is no need, and the same effective medium, that means the HLB tensor for this grain and for this grain will be exactly the same, okay? However, for the phi model, and if the HLB tensor is the same, that means the k is the same for both the interaction tensor. But for the phi model, the k or the interaction tensor depends not on HLB, depends on m bar, which is a macroscopic quantity, okay, or m tilde, which is macroscopic, but depends on m, which is the local compliance, and has orientation. So if the orientation of the crystals, I'm taking here S and M, if the orientations are not the same, then even though the ellipsoid has the same orientation and the same shape and so on, but k still will be different because of the, and this is new, in fact. So there is also the effect of orientation on the interaction tensor. Now, validation of this model will take in different applications. This is we're taking here homogeneous boundary conditions for tension or compression test, okay, uniaxial tension and compression, and that's, I will not show the other for plane strain or for torsion or shear. So if we take here, this is the inverse Paul figure for compression. If I go here down, this is n effective equal n. This is the tangent formulation. And we get this component, this texture component, 100% strain. We can say that all the 110, this is an FCC metal, 110 are parallel to the compression direction. Okay? This is the texture component we get. And we get exactly the same thing if we get a phi equal 0.2. Okay? An intermediate phi. Not too small, not too close to the upper bound. If we take a very small phi, 0.05, which is close to the upper bound, you see the texture, we got 1 fiber, but with some deviation. There is some deviation with respect to the exact 110. Okay? And if we take the secant modulus and the self-consistent, well, you get exactly the same result. Okay? That's why in 1985, we chose to go with the tangent modulus rather than the secant modulus. Now, the same thing if we do tension, okay? If we do tension, this is the tangent formulation, okay? And we got a strong component 111, a strong component 100. So we have, these are the two important components, and we have some other grains in between, okay? And if we take a phi equal 0.5, we get similar results. But if you get the secant modulus, and we compare it to a small phi, which is close to the upper bound, we get exactly 2 components, but we don't get this distribution in between. But this is not a big difference. It all depends how much concentration we have here. But usually the concentration of 111 and 100 is the strongest. So we cannot say much, but the compression talks much better than the tension in this case. Or at least it tells us, gives us more details about the prediction in texture. Now, we looked at also the deviations that we get in terms of the local versus the macroscopic fields, in terms of stress deviation and strain deviation. Okay. Now, if we take the black curve, is the distribution at the beginning of plasticity, just 2%. Okay. So we started with the random, so no surprise to see something more or less spread out. Whereas if you go to 100% strain, where the material becomes highly textured, then you can see this is tension. You can see 2 peaks, in fact. This is because, as I showed you, there are two components of the texture, okay? 2 preferential orientation. That's why you see those 2 peaks, okay? And we see them for stress, we see them also more clear in the strain distribution. And again, we can compare here the tangent modulus versus the secant modulus versus different phi and so on. Another thing is stress-strain curve. Well, I did not start with the stress-strain curve because in these models, stress-strain curve does not tell us much. Because you can use the hardening law in any way you want, put parameters there, and you can fit, okay, whatever you want. That's why I left it to the end, but we keep now the same hardening parameters for all models, okay, for different phi and for upper bound, lower bound with tangent or so. And this is what we get. You know, this is the lower bound, this is the upper bound, okay, and this is for different phi, okay. This is the stress normalized, the equivalent strain, and so it makes sense. This is logical to obtain. There is no surprise, and this shape here is dictated by the hardening law that we have imposed, okay, on the shear rates or the critical resolved shear stresses of different slip systems. Now, one thing we did also is just we took a steel and we tried to fit the stress strain curve, but the steel with different grain sizes, okay? And so we, for these 3 different grain sizes, well, we chose the different phis, okay? I forgot to put the phis here. So the story here is to tell you that phi could be linked to Stockel fault energy, that I mentioned in the beginning of the material, but could also be linked to grain size. So we can maybe link it to Hall patch effect and so on. But we did not go that far. I mean, we are hoping to get some metallurgists to help us maybe link this phi to these microstructural features, could be grain size, Stockel fault energy, and so on. We also applied to many other materials. First results are for FCC, but we also applied for BCC. We also applied for HCP, but I'm not going to show all of these results. This is one of them. This is for BCC materials, and we are looking into the yield locus or the yield function somehow. So this is the yield locus for phi equal 0.1 and phi equal 0.7. So these are 2 extremes somehow, closer to lower bound and closer to the upper bound. And you can see there are some certainly differences, big differences. Now, we choose also, because in BCC, in FCC, we have the 111 planes and the slip directions are the 110, okay? And we have 12. In BCC, the major one is the planes 110 and the direction 111. However, there are also other planes, and there is also even what we call the pencil glide is the 111. We are sure it's the slip direction, and it could be any plane around that 111. So we call the pencil glide. Okay. So here we did not take infinite number. What we took is we took the 110 planes, we took the 112 planes, and we took the 123 planes that are major ones that are known, and that's what we call the pencil glide. Okay, just to have more kinematic freedom somehow. Okay, you have more systems of deformation. But anyway, just to show you that this type of models, we can also predict the yield surfaces, okay? Now, I go to the next application, and that's the polymers and polymer nanocomposites. So I will consider the amorphous and semi-crystalline polymers, but also polymers reinforced by some nanoparticles. I will talk about first the elastic. Sorry. First, I will talk about the elastic constants. This is linear homogenization, and then I will talk about the yield stress, okay? And talk about a model that we developed for the yield stress of different polymers, and we developed it in collaboration with Yves. Now, if we start with the just elastic properties of semi-crystalline polymers, okay, semi-crystalline polymers, you have a crystalline phase, you have an amorphous phase, okay, and it depends on the crystallinity. For polyethylene, for example, if it's low density polyethylene, you have 30–40% crystallinity. If you go to high density polyethylene, you can go to 70–75% crystallinity and so on. So if you take the upper bound or lower bound, this is just averaging of if you want to calculate the effective stiffness, it's just the sum of all stiffnesses, okay? And here the same thing. But now what is the inclusion to consider? So we can think of a double inclusion where we have the crystal surrounded by an amorphous. And there is a paper by Hori and Nimat Nasser that explains well that model that we can apply. We can also use the Mori-Tanaka model. This is the classical Mori-Tanaka where all the inclusions are parallel, but we have here the inclusions, they are ellipsoids, okay, very elongated, okay. So, and they are not in the same direction, so they are all oriented in different directions. And that's why we need to use the generalized Mori-Tanaka, which was developed in '87 by Benvenisti, I think. Okay, so this is the Mori-Tanaka where the effective is the this is the stiffness of the matrix, of the reference medium is the matrix, and times this plus this term here, and this interaction tensor is given by this relationship, which depends on HLB tensor. Okay. We can also use a self-consistent. Okay, and if you use a self-consistent, we use a double inclusion model, and and we make sure that the volume fractions in the double inclusion match somehow some kind of a polycrystal, but a polycrystal made of two-phase inclusions, okay? And in this case, the reference medium is no longer the matrix, like in Mori-Tanaka, but it's the effective medium. So that's why we have this is the effective elastic stiffness, which is given by this relationship here, but the interaction now tensor depends on HLB tensor and depends on the effective stiffness or compliance tensor. All right, application to polyethylene, to PP, to PET, but I will focus only on PE. One thing I would like you to notice here is the crystals are highly anisotropic in these materials. Look at polyethylene. Look at, this is the chain direction, covalent bonds, it's highly stiff, okay? And if you look at the amorphous, the shear modulus of amorphous, very, very low compared to this. So we have a high anisotropy, okay, local. And if you have oriented polyethylene, certainly you will have high anisotropy of your macroscopic material. If it's random, then you will get isotropic answer, but still with this local anisotropy or big contrast that we call it, you cannot rely on upper bound and lower bound. Why? Is because there will be a huge difference between the two. Okay, when contrast is high, then you have to look for intermediate modeling. And we are looking now for Mori-Tanaka and self-consistency to see what they will give us. This is the comparison of the upper bound, you see, a mountain difference between upper bound and lower bound, okay? And this is the Mori-Tanaka, and this is the self-consistent base of this double inclusion modeling, okay? And this is some experimental work. And it looks like the generalized Mori-Tanaka gives us some nice results in this case. However, and the same thing for, this is for for the first one was polyethylene, and this one for polypropylene. Same trend somehow, and we didn't have many experimental results to compare to, but we had only these 2 points. But in 1995 and later in 2007, I developed this two-phase inclusion model, which is just it's like a lamella, but with two phases, with a planar interface, and it just impose the planar or the interface conditions, the jump conditions at this interface, and I used it as my inclusion, and I developed a composite upper bound based on this inclusion, composite lower bound, and also the classical upper bound will be here, the classical lower bound will be here, okay? All right. So, and then based on this inclusion, a self-consistent, okay? And this is the results we got, very nice results actually with this simple model, okay? There is this paper here explains all the details in International Journal of Materials and Structures in 2007. And this is the shear modulus, this is the Young modulus if you want, okay? And we compared to experimental results that we took from the literature. By the way, this model did not come just like that. This model, I developed it in the beginning of the 90s and in the late 80s to simulate large viscoplastic deformation of semicrystalline polymers. And we predicted also texture and so on. And in semicrystalline polymers, you have the texture of the crystal due to the crystal orientation, crystallographic. You have a texture due to molecular orientation in the amorphous, but you have another texture which is morphology, which is the orientation of these crystals. So there is also a couple of papers in 1993, I think, with David Parsk and Ali Argon from MIT that we published on this in a journal, I think, Polymer. Yeah. Now, I move to the nanocomposites. We did some work in Strasbourg with a couple of students on the polymers reinforced with the nanoclay. And the nanoclay comes into particles like this. When you mix with polymers, what happens is, well, depends on the mixing conditions and so on, you may get nothing happens. You still have this micro composite or micro fillers, or intercalation, okay? And this is now much better than so we go to nano somehow. But the best morphology somehow, or microstructure, if you get exfoliation, full exfoliation. And that's what you get the best out of this reinforcement in terms of mechanical properties, okay? So, and in fact, when you see this microstructure, it's like similar to semicrystalline polymers, okay? If you take this as a crystal. Now, for this, we are interested not in the elastic properties, but we did the elastic properties, but I will show you another model. We looked at the yield stress, the prediction of the yield stress. We were interested in a model. There are so many models that exist. One of them is called Argon model, the iron model, and many others. But the problem was they were all valid within a range of strain rate and a range of temperatures, not unified. Okay? So we were looking for a unified model. That's what we developed. What we call here the cooperative model. And in fact, we found some work, an old work by these two authors, and we reformulated what they have done, and by taking the iron model. Iron model has no n here. This term is 1. Okay, we introduced this n here, which is linked to the number of segments in the polymer that are cooperatively in motion during plasticity. Okay, and then we introduced an internal stress as well. Okay, that pre-exists in the material. Now, by doing that, this is what we get. This is the yield stress normalized to temperature, is the internal stress plus this term here, which depends on the activation volume and depends on this characteristic strain rate. The characteristic strain rate, by using shifts, in fact, what happened is the yield will shift if you change temperature, and will shift is if you change the strain rate. So we use these shift relationships here, and we were able to calculate then the characteristic strain rate and link it to the activation energy, okay, and then calculate exactly how this internal stress will evolve with temperature. Okay, so it's a sigma 0 minus m MT. And we set it to 0 when we reach the glass transition. All right. Now this is the final relationship. Now, if the matrix your polymer is all amorphous, well, this is V and this is delta H. But if it is a two-phase, it could be semi-crystalline, or it could be amorphous plus nanoclay. And if you assume nanoclay deforms plastically, okay, like the crystals of the polymers, then we have to homogenize to calculate the effective activation energy, the effective activation volume. Okay, so in this we don't have to go through. This is one-dimensional thing. Okay, and we can use a simple averaging, upper bound, lower bound. Here we use something in between. That's the Mori-Tanaka. Sorry, not the Mori-Tanaka, the Takanagi model. Okay, and by this we used it for semi-crystalline polymers. This is an application to polypropylene. As you can see, we are predicting very nicely the yield stress as a function of strain rate, all ranges of strain rate from quasi-static to dynamic, okay, and several ranges of temperatures. And we also applied it to polymer nanoclay. Well, the nanoclay, we have two different nanoclay, C20 and C. These are two different types of nanoclay, and we were able to predict the yield as a function of strain rate. Of course, here we didn't have dynamic loading. We compared to quasi-static loading, and these are experiments. As you can see, the fit is very nice. Okay, for 1% of these nanoclays and for 5% of these nanoclays. The same thing for the second type of nanoclay, 1% and 5%. Also, the fit is very nice compared to the, at least within the quasi-static. Just keep in mind that this cooperative model, we published several papers. One of them in 2005 with Ivremo and a student of ours, and then many other papers, and we applied it to different polymers, different amorphous polymers, later on to semi-crystalline polymers. So, and the fit is really nice within a large range from quasi-static to dynamic loading, and also from well below TG to around TG, glass transition. Okay. Now, what if the filler does not deform plastically? So I'm not going to calculate activation energy. So what happens is you just take the yield of the matrix and modify it because of the fillers. And the modification, we took this model from these authors, okay, which tells us that the yield of the composite divided by the yield of the matrix is given by this relation. This coefficient, as you can see, is known as Einstein coefficient somehow, but it's multiplied by this term here, which depends on the volume fraction of the fillers, and this coefficient B. Coefficient B will tell us about the somehow the interaction between the matrix and the fillers. If you have exfoliated microstructure, then the B will be very high. Okay. All right. And if you don't have exfoliated, for example, nothing happens. You have microcomposites, the B will be 0. Okay. So we use this in an inverse way. We did experiments for which material here? I think we did some experimental work with the polypropylene filled with the nanoclay, and this is what we get. But this is, we're looking into different strain rates, but just we choose one. Okay, one of them, it doesn't matter which one. Okay, these are 4 different strain rates, sorry. So we choose one. As you can see, this is the parameter B that we calculated through this relationship here as a function of the weight. It is high when the weight percent is very low, which means here we have exfoliation. But when if you go to higher load of the fillers, you don't get everything exfoliated. You have intercalation, but you also have the particles that did not intercalate, did not exfoliate at all. Okay? That means that you can use this to estimate the amount of exfoliation. So that's what we did here. For this case here, B, we find 71. We linked it to the exfoliation 100%. If we have this value here, we got about 17%. So we can use this relationship here to estimate the amount of exfoliation. Now, for the last part, we looked at some biological material, and thanks to Eve, who dragged me into these biological materials a few years ago, and we worked with a couple of students on these projects, maybe 3 students, by the way. But what I will present is just a quick application from one of them for this arthropod quicktail, or which is, in fact, the example is the lobster. We applied to lobster. And in this case, we are using a multi-step homogenization because the microstructure is very complex, and I will show you next slide. And we are interested in just elastic constants. And of course, what we did is look at the effect of interfaces or interphases. Okay, so this is the microstructure of the lobster. Okay, if you go from molecular side to the chitin chains, and then you go higher to the chitin nanofillers and how they are arranged to give us the chitin protein fiber plane, and then these planes you have a twisted plywood to have the final microstructure. But in fact, the final microstructure we can represent it here because we have also voids. Okay, voids in the normal direction. Okay, that are more or less hexagonal voids in the cylindrical voids or hexagonal voids in this direction. And of course, this is the normal. So we're going to look. This is orthotropic properties. We're going to look at the normal modulus and the transverse modulus. So just to show you the multi-step homogenization, first we need the properties at this level here of the chitin chains. Well, we used some work by one of our colleagues with whom we collaborate to do this work. His name is Nikolov, okay, and from Max Planck. And they did also experiments at Max Planck, and we used their experimental work. So they use molecular dynamics to get the elastic constants here, okay? And then from these, we can use these and combine them with the matrix, which is protein matrix, to get the properties of the fibers. And we have aligned fibers in a matrix that is made of proteins, but filled with the calcium carbonate spheres, okay? So we have to do homogenization here to get the property of the matrix. We have to do a homogenization here to get the property of these composite fibers somehow, and then homogenize to get the properties of the one plane, and then average over 3 different orientations and get it to the next level with other pleas, okay? So now with what Nikolov did first, he at these different levels, he used the Mori-Tanaka at this level here. He used Mori-Tanaka used Torquato, Mori-Tanaka again, Voigt and Torquato. This is just to account for porosity. Torquato here used a 2-point probability or statistical method, which is very complex. Actually, it's very difficult to determine those 2-point statistical properties somehow. But what we decide to do is first just use Mori-Tanaka rather than this. And the second thing we decide to do is, instead of using Mori-Tanaka, let's use the self-consistent everywhere, except that here at this level here, when we have to average all these pleas, we just use the lower bound estimate. Now, just to give you an idea of the properties, you have again a huge contrast here in the properties at different levels, okay? This is the elastic stiffness for the that they obtained from molecular dynamics, okay? And these are the properties of the matrix to get the fibers. Now at the matrix at level 3, we have a matrix that has these properties filled by calcium carbonates with these properties, and so on. So we have all the properties here, but the most important thing to retain is we have a local anisotropy, okay, for the chitin at the chitin level, okay, and also we have different matrices here at different levels that have completely different properties, from 4 megapascals, for example, to 37 gigapascals. So these are huge contrasts, okay? So, and we should not be surprised that some models might not work at all, some might work a little bit because of these things. So if we compare now we use the upper bound, this is what you get. This is lower bound. This is for longitudinal, and this is for normal, I call it transverse, but longitudinal, and this is normal Young modulus. And for longitudinal, this is the upper bound, this is the lower bound, okay? Very simple averaging. And these are the experiments by Nikolov, okay? And this is the initial work by Nikolov, okay? And here you have the Mori-Tanaka based, the Mori-Tanaka base gives us lower bound, very close to lower bound, okay? And self-consistent, in fact, as you can see in green, overestimates. So Mori-Tanaka at different levels underestimates, and self-consistent overestimates. So same thing for the normal Young modulus. What we decide to do is just to see, if we can do something at these different levels, at level 3 and level 4, include some interface, okay? Some jump, instead of having a jump between the properties of the filler and the matrix, we'll have an interface that have some intermediate properties and so on. And this is, we use the double inclusion model that I mentioned before, and this is the double inclusion model that was initially developed by Hori and Nimat Nasser in 1993. And again, these are the relationships and so on. I'm not going into these details. By you doing that at this level and at this level, this is what we did, okay? And also at this level here, okay? At this level. However, at this level, the change was not much. Actually, the interfaces did not give us much change. However, at this level, when we include an interface between the calcium carbonate spheres and the matrix, then there is an important effect, okay? And by doing so, here is what we get. We get for the normal Young's modulus, which initially was already not too many, so not much difference in the different cases we looked at. And for longitudinal, we are getting a much better results. However, we really have to tune these results in terms of the ratio between the properties of the filler or the matrix and the interface, okay? And also the amount or the volume fraction of that interface. We have no idea. So we just use tuning somehow. So by this tuning, we can find a compromise somehow to be closer to the experimental results. So with this, I will conclude. So we developed micromechanical modeling for unified constitutive laws that account for microstructural features of heterogeneous materials. We developed also different homogenization techniques for linear as well as nonlinear behavior, accounting for microstructural effects and the evolution. And by using this homogenization, either Eshelby based or non-Eshelby based homogenization techniques, but using also multi-step homogenization procedures. Different materials have been considered: metals, polymers, polymer nanocomposites, semi-crystalline polymers, and biological materials, and so on. And of course, one of the application, and I did not show, is particularly in crystal plasticity, for example, we use the crystal plasticity model to predict the processing path to get to the optimal microstructure that will give you optimal properties, okay? I did not show that. So our idea is, and also for polymers, also polymer nanocomposites, we also use it through this estimation of the exfoliation. So we can use this type of homogenization to get the effective properties, and so to design maybe processes and materials with the optimal properties, and processes such as the 3D printing or additive manufacturing that Professor Allaire had talked about earlier. We can use these kind of modeling, to have a feedback to the process itself, in order to modify the properties of the process or the process parameters and so on. And this just showed me. I'll show you this. This is, in fact, this is an ongoing, we still don't have many results here. This is an ongoing work for application to design of fiber composites built by 3D printing. And here we are using the process called the FDM, fused deposition modeling, or specifically fused filament fabrication, okay, where you have a filament of polymer reinforced by short fibers, but you deposit that, but you deposit along with it long fibers. So it's a mixture of short and long fibers, and we are going to look into these multi-step and multi-scale homogenization techniques to predict the properties in terms of the different reinforcement, but also in terms of the porosity that we get into in these materials. So now, on final note, I would like to thank many of my collaborators in France, in the US, Portugal, Luxembourg, China, and so on. Special thanks go to Professor Yves Raymond, a great collaborator and a great friend, and we have been collaborating for the last 22 years. Okay, and special thanks go to Professor Francisco de Lisola. Thank you for inviting me, and I thank you all for listening. And I leave you with this.
Thank you.
This is Strasbourg, okay?
Yes.
and Professor Raymond had mentioned my stay was on leave in Qatar. I think I have maybe a picture of Qatar, okay? But I was working on a different project. This is the team I was working with, and in fact, this is what I was interested in the photovoltaics. Plus, we were interested also in the water treatment, so we were looking into membranes, polymer membranes reinforced by nano, how to functionalize them and so on. So it's a completely different research project.
Thank you. Thank you so much also for a new point of view about lobster when we will eat the next one we'll see to Professor Ahzi. So maybe we have one question, and yes, please.
Yes, how do you choose the RV, especially the size of RV? Given that RV, the representative volume element, has to be infinitesimal relative to the macro scale, and on the other hand, RV has to be infinitely larger radically than the microconstituents.
Yes, I mean, this is a very important question. Of course, for any homogenization, we have to make sure that the RV is selected correctly. And one way is just to select one size and then increase it until the property is not changing anymore. But I agree with you. There might be some areas in this multi-step where we have to be extremely careful. Okay, we may just using multi-step. There are some length scales that may not allow us to use homogenization because of the limitation of RVE. But yes, we paid attention to the RVE, made sure that the RVE was large enough for the properties not to be changing much.
Thank you. Maybe another question? If not, I propose to have the second break of the morning session, and then we can discuss with Professor Ahzi, of course, and we start for the last plenary session in 15 minutes. Thank you very much again, Professor Ahzi.